Good day, everyone. Today I'll be presenting a research titled Using RoBERTa-based Natural Language Processing to Assess Contributions to Sustainable Development Goals of Academic Institutions. This study explores how we can leverage modern NLP techniques, especially RoBERTa, to automatically analyze academic texts and identify how they align with the United Nations Sustainable Development Goals. These 17 goals from the UN address global challenges like poverty, education, and climate change. Our study explores how academic research aligns these goals using automated natural language processing. Now, our study focuses on academic outputs from three institutions: the University of the Cordilleras, St. Louis University, and the University of the Philippines. We gathered and analyzed research abstracts from these universities to determine how their scholarly work contributes to the SDGs. These institutions represent a diverse range of disciplines and research priorities, making them ideal for this study. To begin, we used RoBERTa, a transformer based model, to classify academic texts based on their alignment with specific SDGs. We also apply NLP techniques like tokenization, TF-IDF, and lexical enrichment to process large volumes of text. This enables scalable automated SDG analysis, ideal for handling thousands of research abstracts. Many institutions produce research on sustainability but lack automated standardized tools to assess SDG alignment. Traditional evaluations are manual, time consuming, and inconsistent, often leading to SDG washing, where contributions are overstated and misrepresented. Now, this study has two main objectives. The first one is to develop a machine learning model that evaluates how well a higher education institution aligns with the SDGs based on its documents, helping assess future sustainability performance. And second, to build a web based tool that lets institutions upload reports or policies and get an automated analysis for their SDG alignment. Now, our methodology follows a three phase process. The first phase is data collection and preparation. We gathered institutional documents such as reports, strategic plans, and policy statements from multiple Philippine higher educational institutions. These documents were pre-processed using OCR, natural language processing, and multi-hot encoding to prepare them for classification. The second phase is NLP model utilization. Here, we fine-tuned a RoBERTa-based model to classify these documents based on their alignment with specific SDGs. We also developed a custom lexicon, LexDG, to improve the model's contextual understanding of region-specific terms. And finally, the third phase is implementation and tool deployment. The model was deployed to a cloud platform and integrated into a web application, enabling real-time SDG analysis and institutional accessibility. Now, in this phase, we collected and annotated documents from 15 higher education institutions in the Philippines. This included reports, policy documents, and strategic plans. To help various formats, we used tools like PyTesseract for text extraction from PDFs and Selenium with Beautiful Soup for scraping web content. The extracted text then underwent through pre-processing, removed noise, standardized words, tokenized the text, applied lemmatization, and removed stop words. Each document was labeled with one or more SDG targets using multi-hot encoding, which allowed our model to support multi-label classification. Here are sample document snippets used during data preparation, each labeled with relevant SDGs. A report on the food support program and one on agricultural knowledge sharing were tagged under SDG 2, Zero Hunger. A passage about scholarships was classified under SDG 1, No Poverty, highlighting educational and economic support. These examples show how institutional texts can reflect measurable SDG contributions, forming the foundation for training our model. To give a clearer picture of the dataset scale, we collected 748 institutional documents from 15 different academic institutions across the Philippines. These documents were then manually annotated with a total of 2,089 SDG labels. Since many texts align with more than one SDG, we use multi-label encoding to capture that complexity. The rich and diverse dataset served as a solid foundation for training our SDG classification model, allowing it to learn from a wide range of real world institutional practices. A key innovation in our method is LexDG, a localized lexicon created for this project. It captures region specific terms like Ilocano or Filipino words such as binadang or kabagis and maps them to relevant SDGs such as partnerships or reduced inequalities. By integrating LexDG into pre-processing, the model better understands the local expressions, reducing misclassifications and improving cultural relevance for Philippine HEIs. This slide shows how the translation pipeline works for LexDG. For example, in the phrase Gawis Kabagis, my friend, LexDG recognizes Kabagis as a culturally meaningful term for comrade. The system standardizes it to good comrade, my friend, preserving its meaning while making it compatible with SDG classification model. Now, this table shows examples of localized terms in the LexDG lexicon. Each word is mapped to its English meaning and related terms to capture its full context. For example, kabadang means partner, companion, or ally, while binadang, common in Northern Luzon, reflects community support and mutual aid. Including these culturally rooted terms helps the model better understand institutional language and improves accuracy for content rich in local expressions. And now, to ensure accessibility and scalability, we developed the system on Google Cloud using Vertex AI and Cloud Firestore. Vertex AI handles the machine learning lifecycle and supports real-time classification via API, and Cloud Firestore manages secure real-time data storage. This cloud setup enables fast access, scalable performance, and cost-effective, secure operation for institutions. The next phase is natural language processing model utilization. This is where we trained and fine-tuned our model to recognize SDG-related content from institutional documents. We divided our dataset into 80% training, 10% validation, and 10% testing to ensure balanced evaluation. RoBERTa was fine-tuned using Python libraries like PyTorch and Hugging Face for multi-label SDG classification. Each document was labeled with one or more SDGs using multi-hot encoding, allowing the model to recognize multiple relevant goals in a single text. This phase gave our model the ability to detect nuanced SDG related content across diverse institutional documents. Now, with the model trained and validated, we moved into the final phase, implementation and deployment, where we focused on making the tool accessible and scalable for real world use by academic institutions. To make the model accessible, we built a web hosted application with a Flask API backend. Users can upload documents through the interface, which are then processed and classified in real time by our RoBERTa model. This design allows academic institutions to assess their sustainability reports quickly without needing technical expertise or heavy infrastructure. We evaluated the model using precision, recall, F1 score, and accuracy. Precision shows how many predicted SDG matches were correct. Recall measures how well the model finds all relevant content. F1 score balances precision and recall, and accuracy reflects overall prediction correctness. These metrics together assess how reliable the system classifies documents by SDG alignment. Now, with our model trained and performance validated, we then focused on building an accessible and scalable deployment. This involved connecting the model to a cloud-hosted web application for real-time document classification. Now let's take a look at how the system actually works. Now here's a simplified overview of the workflow. The users start by uploading a document through our cloud-based website. The web app built on a Node.js server takes the document from the user and sends it to the RoBERTa model via a Flask API. The model processes text, classifies it according to relevant SDGs, and returns the results. Finally, the web application displays the classification output to the user, quickly and with minimal technical effort required. All of this runs on Google Cloud Platform, making it both scalable and efficient for institutional use. This is the homepage of our web app. It is simple, and the user-friendly design lets institutions upload documents easily. Users can start classifications with just a few clicks, making it accessible even without technical expertise. Our goal was to build a powerful yet easy to use tool for sustainability workflows. Now, here's an example of how the system identifies and classifies content. This institutional initiative by St. Louis University focuses on providing access to food security. Our model successfully recognized this document as aligning with SDG 2, Zero Hunger, based on keywords and context such as food access, sustainability, and community outreach. This illustrates how the system interprets real documents and connects them to relevant SDG themes with minimal human input. This slide shows the Ilocano phrase Saranaite alumni, which translate to alumni aid or support. Without cultural context, a model might overlook its importance or misclassify it. However, by using LexDG, the system accurately recognizes this phrase, maps it to relevant concepts like alumni aid, and links it to SDG number 2, Zero Hunger, reflecting efforts in community food support. This example highlights how LexDG enhances the model's ability to interpret local language nuances and connect them to global sustainability goals, improving classification accuracy. This bar chart compares the model's performance with and without the LexDG lexicon. As you can see, when LexDG is integrated into the RoBERTa, the F1 score significantly improves from 0.68 to 0.74. Now, this highlights the value of incorporating localized domain-specific knowledge into a natural language processing tasks. Without LexDG, the model struggles to interpret regional expressions and context, leading to misclassification. It is a clear case for why cultural and linguistic context matters when analyzing documents from diverse academic institutions. Now next, here we see the lowest F1 scores from our evaluation. SDG 2 Zero Hunger scored 0.55, followed by SDG 4 at 0.61, and SDG 11 at 0.66. These lower scores reflect challenges in distinguishing overlapping themes, like food security appearing in both education and poverty contexts. Improving these results will require refining our lexicon and enhancing the model's contextual understanding. Now, this table compares RoBERTa with traditional machine learning models. Logistic regression and SVM performed reasonably well, but BERT showed clear improvements, especially in precision and F1 score. However, RoBERTa outperformed them all, achieving 96.77% accuracy and the highest F1 score at 0.74. This confirms that the transformer-based models, particularly RoBERTa, are more effective for complex multi-label SDG classification tasks. Now, our system provides several key benefits for higher educational institutions. First, the web app offers real-time SDG classification for immediate sustainability tracking. Second, it automates assessment, reducing manual tagging and review. Third, it enables dynamic tracking of SDG contributions to support better reporting. And fourth, it's scalable and user-friendly, providing a standardized tool for analyzing documents across institutions. Now, our model showed strong performance with high accuracy across most SDGs. The web app made the system practical, allowing easy document uploads and clear result displays. Overall, this tool can support ongoing SDG monitoring and planning efforts of HEIs, helping institutions align their initiatives with global sustainability goals more effectively. While the results are promising, there's room for improvement, especially for SDGs 2, 4, and 11, which had lower F1 scores. Future enhancements will focus on data augmentation, better pre-processing, and more domain-specific fine-tuning. These steps will help improve classification accuracy, and make the system even more effective for real-world use. Thank you.